Well, let's start. Let's get going with the second day. And we have two wonderful Zoom talks before lunchtime. And then after lunchtime, Javier will speak. This morning, we have first Enrique Becerra and then Carlos Simpson. And so it is a pleasure to introduce Enrique Becerra from CINVESTAV, Mexico. And he's going to be speaking about the chiral cyclic complex of a Calabi-Yau category. Enrique?
Thank you. I'm very happy to being able to speak here today, and I would like to talk about some ideas that we are exploring in joint work together with Professor Ludmil Katsarkov and Ernesto Lupercio. And so this is still work in progress, but let me start. So let me begin with some motivations. So the guiding question that we are asking is the following one. So we ask if there is a way to extend the notion of elliptic genus into the non-commutative setting in a way that it reflects the underlying, let's say, conformal field theory associated with such a non-commutative space, as I will explain a little bit more precisely later on. So, in one hand, for smooth, let's say, complex varieties, we have a geometric way to define an invariant, which is called the elliptic genus. But there is also a corresponding notion of the elliptic genus of a conformal field theory in physics, which is defined as a partition function of such a theory. So in this setting, the so-called Chiral De Rham complex, as I explained, provides in some way a categorification of this invariant given by the elliptic genus. And so our goal here will be to explain how this picture could be extended to the case of a Calabi-Yau category. And we will construct a corresponding vertex operator algebra, which allows us to produce such a non-commutative version for the elliptic genus. So this is the motivation for the rest of the talk. And okay, so the main idea that I or that we proposed is as follows. So suppose that we are given a Calabi-Yau differential graded category with some maybe with some additional properties, which allow us to think of such an object as a non-commutative version of an algebraic variety, and we would like to construct a vertex operator algebra, which we call the chiral cyclic complex associated with this category, which deforms or quantizes in some way the periodic cyclic complex of the category. So the construction is based on some constructions that we can perform out of such the DG category, which are given or can be expressed in terms of Hochschild chains and cochains associated with the category. And we also use in a strong way the Calabi-Yau structure to produce an object which we try to deform or quantize in order to produce the vertex operator algebra that we would like to produce out of this data. And following the work of Costello and William, so we will use in some way or in some following this work of Costello and William, we use the Batalin-Vilkolbisky formalism in order to quantize our object and produce the chiral cyclic complex. So the expected features of the object that we get out of these constructions is that so in the first place we would like to produce some vertex operator algebra out of these things, but moreover we also like to verify that this vertex algebra has some additional structure, which is called an n equal to 2 superconformal structure. So this additional structure is absolutely necessary in order to being able to produce the elliptic genus out of this guy. And moreover, we can phrase this idea that this provides a deformation of the periodic cyclic complex by verifying that the conformal weight zero piece of the vertex algebra that we construct reproduce or recovers the periodic cyclic complex of associated to the category. And additionally, the cohomology of this vertex operator algebra with this additional structure, which is called the BRST cohomology. Then, since we identify the conformal weight zero piece with the periodic cyclic complex, at the end we will recover the periodic cyclic homology of the category. So this is more or less the proposal that we have and the idea to construct this kind of thing. And so let me explain with a little bit more detail about this construction. So let me just say some words about how the elliptic genus is usually defined in the setting of conformal field theory, and also I will explain a little bit how this is or can be defined or constructed geometrically in the classical setting. So in terms of the of a conformal field theory, we can produce an invariant of this of such a conformal field theory as an index in some way, as the trace of some operators which are included in the structure of a superconformal field theory. So we have some space of states of the theory, and we also have some operators on this space which have some interpretation in terms of the physics occurring in this conformal field theory. So we have these three fields which are related with the Hamiltonian or energy of the theory, and we also have some fields encoding some additional structure, which is or can be interpreted as a sort of charge in this setting. So in this Hamiltonian or energy operator in the theory, decompose the state space into conformal weight pieces by taking the spectral decomposition of the operator, and we also have the corresponding spectral decomposition given by the U1 charge here. And the idea is that more or less by taking the Poincaré series associated with such a decomposition, or if we take the graded dimension of these pieces given by the eigenspaces of these operators, then we can produce a partition function of the theory, which by definition is the elliptic genus associated with with such a theory. So this turns out to be an holomorphic invariant of the theory, and it behaves nicely with respect to continuous deformations or deformations of such a theory. So this is more or less the physical perspective of this invariant, but there is also a geometric interpretation of the elliptic genus, which can be phrased as follows. So the heuristic interpretation of this invariant is due to Witten, and the idea is that so if we start with a variety or a space, then the elliptic genus can be interpreted or has an interpretation as the index of some Dirac type operator on the free loop space of the original space. So we start with some, let's say, variety or some classical commutative space, and we can, so in good circumstances, we can define some operator um, which corresponds in some way with the idea of taking the Dirac operator on this formal loop space or free loop space, and the index of such operator will recovers the elliptic genus of the variety. Okay, so this encodes the strange geometry in the loop space is included in this picture, and so we are encoding in some way the stringy geometry of X. So on the other hand, in more classical terms, if we start with smooth complex variety, then we can write down the elliptic genus of the variety in terms of characteristic classes. So there is an expression using the so we can use the Atiyah-Singer index theorem, or we can reinterpret this formula in terms of Hirzebruch-Riemann-Roch theorem, and we can write down the elliptic genus of the variety in terms of characteristic classes like this. So the idea is that this is defined for smooth complex varieties, and this genus, which at the end will produce some formal power series in two variables or some function which depends on two complex variables, refines in some way some classical genera like the Hirzebruch polynomial or the eighth class of the variety, and so this is sensitive to the smooth, or sorry, to the complex geometry of X. So this is more or less the geometric picture, and so in order to relate this definition or this way to write down the elliptic genus in terms of characteristic classes with the heuristic picture of the elliptic genus as the index of some Dirac type operator on loop space, there is a way to construct an infinite dimensional bundle over X, which is related with the index interpretation of a loop space using so this infinite dimensional bundle that is right down here relates in some way, or the idea is that this infinite dimensional bundle provides a relation between the elliptic genus writing in terms of characteristic classes and the loop space interpretation. So the main point that we can point out out of this infinite dimensional bundle here is that this is divided in two parts. So one of them corresponds to the so-called bosonic modes of the theory, which are related with the symmetric powers of the tangent and cotangent bundles. And on the other hand, we also have a part or a sector of this infinite dimensional bundle, which is related with the fermionic modes, which are given in terms of exterior powers of the tangent and cotangent bundle. So this infinite dimensional bundle has a decomposition into graded pieces in such a way that each graded piece is related but can be write down in terms of a combination of symmetric and alternating powers of the tangent and cotangent bundles. And these will be important in order to being able to generalize these ideas to the non-commutative world. So the interpretation of this kind of decomposition is that this resembles in some way a focus space built up out of the direct sum of the tangent and cotangent space or cotangent sheaf of the variety, and we would like to mimic this kind of construction in the non-commutative setting, as I say. Okay, so moreover, in the Calabi-Yau case, so if we have a Calabi-Yau variety X, the elliptic genus turns out to be, so the elliptic genus moreover has some modularity properties which are related with the conformal invariants of the theory. So in the Calabi-Yau setting, we can enhance this structure with something called an n equal to 2 superconformal structure. And this implies that the elliptic genus associated with X in this case has some nice modularity invariance properties. So the idea is that the elliptic genus is not just a plain numerical invariant associated with the variety, but moreover encodes some deep geometry and the conformal structures associated with the variety, with the original variety. Okay, so so in order to relate in some way the geometric picture that I described, so there is a way to relate this geometric interpretation of the elliptic genus in terms of loop space and this focus space associated with some of the tangent and cotangent spaces and the physical or the superconformal version of the elliptic genus. And this, so the machinery that we can use in order to produce such connection between these two ways to look at the elliptic genus can be phrased in terms of, or can be put in terms of some algebraic structure which is called a vertex operator algebra. So so the idea is that we would like to start with some geometric setting given by maybe a Calabi-Yau space, and we would like to produce out of this space a superconformal field theory in such a way that the index or the character of these of the vertex algebra associated, the chiral algebra associated with this superconformal field theory reproduce the geometric elliptic genus. And the way or a way to do this is through the notion of the Chiral De Rham complex, as I explained now. Okay, so given a smooth complex, let's say algebraic variety, but it can be a smooth complex variety, not necessarily algebraic. So the Chiral De Rham complex is a sheaf of vertex operator algebras on X, and this construction was introduced by Malikov, Sedgman, and Weintraub, and locally has a nice local description in terms of free fields associated with the local coordinates or the local geometry of the variety. And these constructions involves or combines the local geometry of the variety, vertex operator algebra theory, and the conformal field theory interpretation of these things. So let me just describe very briefly how is the local description in terms of free fields of the Chiral De Rham complex. And locally, this sheaf of vertex operator algebra is generated by two types of fields, which are given by bosonic ones and the fermionic bosonic fields and fermionic fields. So the first pair of the first two terms here, the bosonic sector of this thing, is called the beta gamma system, and is associated, or this is related with the coordinates and the vector fields, the local coordinates and the local vector fields of the variety. And on the other hand, so this is the bosonic part, the first one. And then we also have something called a BC system associated with or related with local differential forms of the variety. And so this produce in some way or reflects in some way this Fock space associated with the sum of the tangent and cotangent spaces. And so these fields encodes in some way the geometry of this object, the sum of the tangent and cotangent spaces, locally at least. So yes, as I said, it is local fields associated with or given in a local coordinate patch of the variety are related with the local coordinates and also the local vector fields associated with these coordinates, and also the differential forms of this local coordinate on the variety. So the case structure here will be this object here, as I said, and this kind of construction suggest an additional structure that we can that keep track of all these construction in terms of or which provides a more representation theoretic flavor of this thing. So this suggests that there is a kind of something called a Manning double structure on this thing. So recall that the idea is that there is in some way a Fock space structure associated with this geometric object given by the tangent and cotangent space, and out of this we build the modes of the free fields associated with coordinates, vector fields, and differential forms, and this will produce an infinite dimensional bundle, as I say. And so this is exactly the kind of structure which appears in the construction of the elliptic genus. So there is a deep relation between the construction and the geometry involved in the construction of the Chiral De Rham complex and the definition the definition of the elliptic genus in terms of characteristic classes and the loop space interpretation. So in some way, so we can phrase this by saying that in some way the Chiral De Rham complex associated with the variety X can be viewed in some way as a sort of quantization of the formation of the Manning double given in terms of the tangent and cotangent space. So we have a natural pairing between these two objects, and we can endow these things with a Manning double type structure. So the chiral De Rham complex as a vertex operator algebra or a sheaf of vertex operator algebras can be viewed as arising out of this quantization of the classical data given by this Manning double type structure. So, moreover, the additional n equal to 2 or additional supersymmetric structure which the chiral De Rham complex carries. So in the case of a Calabi-Yau variety, moreover, the chiral De Rham complex has this additional n equal to 2 superconformal structure. So locally, we can define, besides these local fields given in terms of coordinates, vector fields, and differential forms, we can define locally out of these basic fields some additional charges or some additional fields which are well defined locally. But it is not true in general that this additional supersymmetric structure which appears in local coordinates can be globalized to the whole variety in order to produce n equal to 2 superconformal structure, which is necessary in order to define the elliptic genus of the variety in terms of the superconformal field theory that arise out of this data. So, but in any case, in the Calabi-Yau setting, so if X is Calabi-Yau, all these local fields can be globalized, and we obtain a sheaf of vertex operator algebras, which also has this additional n equal to 2 superconformal structure. So in the Calabi-Yau setting, we can do this, and this reflects the geometry of the variety, and moreover, we also have due to this additional supersymmetric structure, we has these nice modularity properties of the character of such a vertex algebra, which are at the core of the elliptic genus. So in this Calabi-Yau case, the great character, and so this way to look at the elliptic genus in terms of a character of a vertex operator algebra is, of course, or resembles the superconformal theoretic viewpoint of the elliptic genus. And so this the elliptic genus defined in this way is a partition function associated to the theory, which is encoded in the vertex algebra structure of the chiral De Rham complex. And in this way, we can interpret in some way the chiral De Rham complex as a kind of categorification of the elliptic genus in this way. So the road to go from the geometric definition of the elliptic genus and the superconformal field theoretic way to define the elliptic genus is moreover like this. So we start with a geometric object, and then we can produce a vertex algebra which will correspond to the chiral algebra with some superconformal field theory associated with the geometry of the variety. And this is obtained by deforming in some way or quantizing in some way a structure which is or can be written down in terms of the geometry of the variety. And then we can produce some invariant by taking the character of such vertex algebra. So this in this way we relate the geometric definition of the elliptic genus and the field theoretic or conformal field theoretic way to define this thing. So moreover, this deformation or quantization of the geometry given by the Manning double associated with X can be phrased or can be interpreted as a kind of affinization in the of this Lie type structure. So this Manning double has a Lie type structure, and we can so in the language of representation theory we can produce the affinization of this Lie theoretic structure, and this will provide this deformation or quantization of this classical geometry. And so this quantization procedure will we can construct out of this quantization procedure a vertex algebra. So moreover, the idea is that this affinization can be interpreted as or can be done by taking into account two things. So we produce in some way some local fields or some field theory associated with the geometry, and then we quantize this thing. And so this is the road that we will take in order to generalize these constructions to the non-commutative setting. Okay, so this affinization construction, so the general picture of this kind of affinization structure of a Lie theoretic structure is moreover like this. So we start with some Lie algebra, let's say. In very broad terms, we start with some Lie algebra, and then out of this algebra we construct or we produce another Lie algebra, which is called the formal loop algebra associated with G. So we start with this Lie algebra G, and then we construct the loop algebra, the formal loop algebra associated with G, and then we proceed to quantize this loop, this formal loop Lie algebra. So this quantization can be phrased in terms of the representation theory of the loop algebra. So we construct some module or some focus space out of this formal loop algebra G, and this module over the formal loop algebra can be endowed moreover with the additional structure of a vertex operator algebra in such a way that the space of states of this vertex operator algebra is given by some module that we consider and that has an interpretation as a Fock space. And so this kind of construction can be interpreted as a kind of quantization. So we would like to do something similar in the non-commutative setting. So let me explain how this could be done. So the idea is that so even if we cannot so the classical Chiral De Rham complex can be write down as this as an affinization of the Manning double given by the sum of the tangent and cotangent space of the variety, and so we can more or less take this or make this affinization process in order to produce a vertex algebra out of this data. But yes, so in order to phrase these kind of constructions in a way that is more amenable to generalize this to the non-commutative setting, we interpret this kind of affinization in as these two processes. So we construct these local fields, dimension 2, let's say, over the disk, and then we quantize this classical field theory, and this process can be interpreted in some way as a sort of affinization. So well, yeah. So the idea for the formalism which allow us to perform such kind of this sort of affinization process interpreted as a sort of quantization following the constructions of Costello and William is the Batalin-Vilkovisky formalism. So more or less, we can think of this formalism as follows. So in let's say classical mechanics, we have some Poisson algebras or Poisson manifold, which is which provides the observables or the algebraic structure encoding the observables of the classical theory, and we can deform or produce the quantization of such a system by the construction as a sort of well, we can quantize this classical system following this deformation quantization procedure, which allow us to start with a Poisson manifold and then produce some associative algebra, which deforms the original product of the algebra of classical observables. So, in some way, the Batalin-Vilkovisky formalism allow us to do such kind of deformation quantization procedure, but this time not with a classical mechanical system, but with a field theory. So we have a field theory which is infinite dimensional. So the state space now is infinite dimensional. So we would like to produce some kind of deformation quantization of the observables of this two-dimensional field theory. So so the Batalin-Vilkovisky structure associated with this algebra of observables of this field theory can be interpreted in some way as a kind of, so we can interpret this as an analogous of the Poisson algebra structure on the algebra of classical observables. So we start with such a with this kind of point of Poisson algebra structure on the space of observables, and so the Batalin-Vilkovisky formalism allow us to perform in some way a kind of deformation quantization of this structure. So in our setting, we will start with a Lie theoretic structure. So we will start with a Lie infinity algebra or a Lie algebra up to homotopy. And moreover, this algebra will be endowed with a cyclic structure, with some additional structure which allow us to produce out of this cyclic structure on a Lie infinity algebra Batalin-Vilkovisky theory, which encodes the algebra of observables of a field theory. In our case, a two-dimensional field theory over the disk. So these higher brackets and the compatible pairing that is included in this structure given by a cyclically infinity algebra structure allow us to construct such a BV theory. And okay, so in our case, the kind of or the affinization that we would like to perform will be given like this. So we will start with this Lie infinity structure with an additional cyclic structure, and we will produce out of this Lie theoretic structure a space of local fields over the disk, and then in some way this can be interpreted as so if we try to relate this with the affinization picture that I described, this will produce in some way or is related with the formal loop algebra construction. So so the construction of a space of classical fields resembles in some way the construction of the loop algebra of the Lie algebra that we start with. This is which is given in terms of the Manning double of the geometric space, the non-commutative space, as I explained. And so this DD formalism allows us to start with this kind of algebraic structure and produce, in some cases, in good cases, this allows us to produce some kind of deformation quantization of this classical structure. Okay, so so at the end, this will produce the space of observables, or the algebra of observables in this quantization of the original classical structure, and moreover, this allows us to produce something called a factorization algebra over C in this case. So we will construct a factorization algebra on C, or on the complex plane, out of this deformation quantization procedure. And so this will, so the idea is that this factorization algebra that emerge of that we can extract out of the quantization procedure is will be related with the vertex operator algebra that we would like to produce. Okay. So the connection or the relation between factorization algebras and vertex algebras is due to Costello, and these factorization algebras turns out to be related in a deep way with vertex operator algebras in some cases. So in the case of a factorization algebra over C, which satisfies some holomorphic and invariance conditions with respect to loop rotations or rotations with respect to the circle action on C, then this factorization algebra produce vertex operator algebra, and so the moreover the process will be like this. So we start with the DB theory, which is defined in terms of the Manning double associated with the geometry of the original space. We will produce, using Costello, William, and formalism, a factorization algebra as a sort of quantization, and then we verify that this factorization algebra that we construct satisfies some holomorphic conditions, let's say some invariance with respect to loop rotations, and this will allow us to produce out of this factorization algebra a vertex operator algebra. Okay, so this is more or less the idea, and so yes, let me explain very briefly how this works in the case of a non-commutative space. That is the main motivation for us. We would like to apply this kind of framework to non-commutative geometry, and so we will replace the Manning double given by means of the tangent and cotangent space in terms of Hochschild complexes associated to the space. So we will use this additional Calabi-Yau structure on the category in order to define a Batalin-Pilkowski classical field theory, and by deforming this, or by making some deformation quantization of this classical field theory, we will produce the Chiral Cyclic Complex associated with the non-commutative space. So very briefly, let me just remind you what is the philosophy behind non-commutative geometry. And so the idea very briefly is that algebraic geometry can be extended by replacing spaces with categories. So in this world, spaces, by space we mean some sort of category or linear category, and we consider DG categories or A infinity categories up to Morita equivalence. So these Morita equivalent classes of DG categories corresponds to the spaces or the non-commutative spaces that we would like to consider in this setting. So the geometry is encoded in the homological data associated with such a category, and the main or the key example of all these philosophy is the category of perfect complexes associated with a variety X. So we can replace in some way the original space by the DG category given by the by perfect complexes on X, and the idea is that we would like to make or to extract the geometric information of X out of this object in purely categorical or homological terms, in such a way that we can interpret general DG categories as a sort of space in this setting. So the parallel notion of a Calabi-Yau variety in this non-commutative setting is given by the notion of a Calabi-Yau category. So very roughly speaking, this means that we have an analog of the volume form of this kind of non-commutative space, which provides or gives some duality in this categorical setting. Moreover, Calabi-Yau related with something called topological conformal field theories, and in some way they are equivalent. So there is a close connection between Calabi-Yau DG categories and the idea of a topological conformal field theory in this way. So out of these, or we can interpret using these equivalents some constructions or homological algebra constructions on the category in terms of the let's say physics of this topological conformal field theory. So we have on the one hand the Hochschild co-chain complex associated with the category, which correspond to the open sectors of the topological conformal field theory, and we also have the Hochschild chain complex, which is related with the closed sector. Okay, so geometrically, this corresponds. So the Hochschild co-chain complex corresponds to the, or can be interpreted geometrically as polyvector fields on this non-commutative space, and Hochschild chains can be interpreted as a replacement in this non-commutative setting of differential forms. So we have these two basic ingredients, which are the basic data that we need in order to produce a sort of Lie algebra structure which resembles the Manning double in classical geometry given by tangent and cotangent space. And so moreover, these objects are closely related with the derived tangent complex of the non-commutative space, and also has an interpretation in terms of the derived loop space of A. So the analogy is that Hochschild co-chains will correspond with polyvector fields that will be associated with the tangent space of X, and the Hochschild chains will be related with differential forms. So moreover, we have an additional cyclic structure given by Cohn's operator on this complex, and we will produce, or we can produce out of these Hochschild and co-chains and chains, we can produce a mixed complex, which moreover produce at the end a complex which is the non-commutative analog of the De Rham complex of the space. So this periodic cyclic complex, the idea is that the periodic cyclic complex is the non-commutative analog of the classical De Rham complex of a variety. So, moreover, this encodes some additional symmetry by making by taking rotations. So this cyclic structure is encoding an S1 symmetry on Hopfield complexes, and so this periodic cyclic complex can be viewed in some way as a sort of equivariant S1 object that is constructed out of these things. Okay, so this incorporates loop rotations. And okay, so the Calabi-Yau structure. So if we impose an additional Calabi-Yau structure on our category or on non-commutative space, so we have an additional pairing between chains and co-chains, and this is all compatible with the cyclic structure here. And so we can take these the sum of these shifted versions of the chain and co-chain Hopfield of the non-commutative space. So this is the elliptic object that we would like to use instead of the Manning double in the classical setting. But this time we need to work in the homotopical or in the homotopical versions of these algebraic structures. So, moreover, this homotopy Manning double is endowed with a Lie infinity structure, and also in terms of the Calabi-Yau pairing, we can impose some cyclic additional structure on this Lie theoretic structure. And so the idea is, again, by using the VB formalism, we can construct two-dimensional field theory out of this Lie theoretic structure and quantize it in order to produce the object that we are interested in, which is this deformation of the periodic cyclic complex. So I think that I don't know if I have time, or how much time do I have?
5 minutes.
5 minutes. Okay. So, well, yes. So, so basically, this is the idea. The idea is that we can use the very same formalism which allow us to interpret the construction of the chiral De Rham complex in commutative geometry as a sort of affinization. And so this affinization, can be phrased in terms of deformation quantization of a field theory or local field theory on the disk, which is encoded in this Batalin-Vilkovisky structure on the Manning double. And yes, so of course, in order to being able to quantize this structure, we need to verify in this case that so in order to this quantization procedure to being able to produce this deformation quantization, we need to verify we need to verify that the obstructions of such a deformation vanish. But so the idea is that this can be done using the additional Calabi-Yau structure on the category that we are imposing in our setting. So, moreover, we also have some additional structure on the deformed periodic cyclic complex that can be written down in terms of the Hopfield and Cones operator in such a way that the final object that we get, which is this factorization algebra of observables, satisfy this holomorphic conditions that we need in order to produce a vertex algebra structure. And moreover, we also need to verify that the final structure that we get also has the n equal to 2 superconformal structure that we need in order to being able um, to define an elliptic genus in this case. The idea that this provides a deformation of the periodic cyclic complex can be stated in the following way. So one of the main properties of the chiral cyclic complex that we construct is that the conformal weight zero component of this thing recovers the periodic cyclic complex. So in this sense, the periodic cyclic complex emerged out of this deformation of the Manning double structure we start with. So we start with this Manning double structure. We use the BB formalism to quantize or deform this, and we can recover the weight zero as a weight zero component, the periodic cyclic complex associated with the variety. And moreover, the additional data or the additional fields that are included in our construction recovers, for instance, the periodic cyclic homology of for space as the BRST cohomology. So this is parallel to the so there are parallel results in the commutative or classical setting in terms of the Chiral De Rham complex. So the Chiral De Rham complex or the cohomology, the BRST cohomology of the Chiral De Rham complex recovers the usual De Rham cohomology. So in this case, the BRST cohomology recovers the periodic cyclic cohomology, which is the analogous of the De Rham cohomology. And yes, so as I said, the additional n equal to 2 structure, moreover, allow us to define a sort of superconformal field theoretic notion of the elliptic genus of a non-commutative space in this way. Yeah, so there are some compatibilities with the classical picture. So the expectation is that we start with the category of perfect complexes of a smooth Calabi-Yau variety. Then this elliptic genus we define using the chiral cyclic complex recovers the geometric elliptic genus of the variety, and we also so we can apply this construction to other other Calabi-Yau categories which does not come from geometry. So for that that are not constructed as the category of perfect complex on a classical space. So for instance, we would like to use this mechanism in order to produce the elliptic genus of a singularity by taking or by considering the category of matrix factorizations associated with the singularity. And so we can produce an elliptic genus using this construction in this case as well. So this also can be done in other contexts. Okay, so yeah, I think that I will stop here and thank you.